Labs, Aviation and Space. She studied physics at the University of Genova in Italy and did her PhD on radiation protection of astronauts in missions to Mars as part of the European Space Agency. She continues to lead projects from here at CERN in Geneva in Switzerland, while also teaching and conducting public outreach activities, which she's very passionate about. So please, everyone, welcome Associate Professor Susanna Guatelli.
Hello. Hello. I'm happy to be here with you, and I would like to thank you for this invitation. Okay. Yes, so today I will talk about challenges of a human mission to Mars by a radiation protection point of view. So manned missions to Mars have been identified as a main goal by the International Space Exploration Coordination Group, which includes 15 space agencies, including the Australian Space Agency. I would like to mention that through all my talk, you will see references to websites. Well, these links are for you if you'd like to have more information, because I will what you will hear today, a lot of it is public information which is distributed by NASA. So you can find documentation on the web, scientific documentation on the web about what I will be talking today. So the roadmap to a human mission to Mars started with the International Space Station since the 2000. So the International Space Station is an international lab which is in the low Earth orbits. As you may know, it hosts about 5 or 6 astronauts every time, and about 2,000 scientific activities have been implemented there. So these activities range a lot of different applications, from biology, chemistry, physics, and medicine. But ultimately, the importance of the International Space Station is that it's a test bed. It's a test bed where we can study the science and where we can test the technology that could be then used for missions, human missions to the moon and then also to Mars. So we have the International Space Station, and then in the roadmap that has been defined, the moon is the second step. So a mission to the moon is envisaged for the 2024 to 2025. And the idea is to establish an outpost there. An outpost that will allow us to perform experiments, and also to study technology that can be used then in missions to Mars. And then finally there is Mars. Mars, this is the map of the solar system, not to scale. You can see here, I don't see my here. This is the Earth, and then we have Mars. Mars is a little bit small, is smaller than the Earth, and is the 4th planet, let's say, of the solar system, starting, let's say, from the sun outwards. So Mars, a mission to Mars is envisaged for the 2030s. Why to go to Mars? Well, I suppose it's for our instinct to explore, and this idea, it's years and years that we talk about going to Mars. I mean, I've done my PhD. I finished it in 2008, and still already missions to Mars were very hot at that time. There are various designs of a mission to Mars. In this talk, I will refer to a particular one of NASA. In this human journey to Mars, we have a round trip of at least 2.5 years. So let's say 2.5 years, 3 years of emission. So we have 6 months to fly to Mars. Then the astronauts had to stay there at least 1.5 years. And then it's another 6 months to come back. So this is one of the design. So it's about 2.5 years, 3 years in a mission to Mars. Now I would like that you take your mobile phone or your computer, if you like, and you go on this website, live.voxvote.com, and you put this pin 37648. Please do it. I will wait some time. And what you should see, if I can find it. Okay, let me share my screen so it will be easier. So you should see this question. So please go in this website, live.voxvote.com, and type this pin. I will also include it in the chat. So the website is live.voxvote.com, and the pin is there, and I include it in the chat. I will give you still some moments. If you can please write to me in the chat if when you manage to be there. Okay, some already started. I will wait a little bit longer. So the question that I would like to ask to you. Excellent. I start to see some done. Is this one? If you could, would you go to Mars in a 3 years mission? So this is my question for you. I will give you some time to answer. It's a yes or no. No maybes, yes or no. Time is up. Wow, we have a 50% yes and 50% no. So let's see what will happen during the seminar if I manage to, if you will change your mind or not. So let me go back to my talk. Can you see my talk? I suppose it's a yes. Oh, yes, thank you very much. So which are the risks for a mission? Which are the risks associated with the presence of humans, of astronauts in space? So there are, first of all, physiological problems due to a reduced gravity. We are built to live on our planet and to this, let's say, to our gravitational fields, and so when we have a reduced gravity, this causes problems to our body, to our muscles, and to our bones. Then there are also psychological problems caused by isolation. And another one, the last problem, is acute and late risks to the health of astronauts caused by exposure to radiation. And today I will talk on these acute and late risks of radiation. So my talk will be about that. But first of all, we need to understand what is radiation. Well, radiation is energy or particles that travel through space or other media. Let's say through space. So an example is light, is radio waves. Heat is a radiation. But then light, heat, microwaves, they are all examples of electromagnetic radiation. Then we have also particles like protons, electrons, nuclei of helium, and nuclei in general, nuclei of atoms. So you have to think about atoms where all the electrons have been stripped out and you only have the nuclei. Well, in space, there are all these particles. We have electromagnetic waves, we have protons, we have helium nuclei, and we have also heavier nuclei that travel in space. If we look at, in this slide, I indicate which are the radiation sources which pose a threat to astronauts in terms of Earth. We have solar energetic particles. Okay, we call them also solar particle events. And we have that the sun generates these winds of particles. They are mainly protons, and we call it the solar winds. And they are can be pretty intense. And are indicated by these yellow arrows. So then we have the galactic cosmic rays. Galactic cosmic waves, galactic cosmic rays are a background radiation, and that derive from our solar system and beyond. Their origin is associated with the explosion of supernova, and these galactic cosmic rays are mainly protons, 75%. Then we have about 24% of helium nuclei, and then 1% all the other elements. So we have carbon, iron, silicon, iron nuclei. But the Earth has a geomagnetic global magnetic field. So what happens is that when all these, the charge, when the solar wind, when the galactic cosmic rays, they are incidents on the magnetic field of the Earth, basically they are diverted and they will not reach us. So basically our magnetic field, which is represented here by these blue lines, acts as a shield that protects us from the harmful effects of radiation. In addition, our atmosphere stops a lot of the electromagnetic radiation that comes from the sun, like the ultraviolet lights. But Mars is different. Mars is smaller, so it means that its gravitational field is smaller than the Earth. This means that the atmosphere is thinner. And if it's thinner, it means that we have a larger amount of ultraviolet light and electromagnetic radiation that is incident on the surface of the planets. And then Mars, we do not know why, and this is a mystery, there is a global magnetic field. This means that there is not a magnetic field that shields the planet from the space radiation. Space is a very harsh place by a radiation point of view. So in this slide, I would like to describe to you which is the interaction of radiation with the DNA. The hypothesis is that radiation causes damage to the cells when it interacts with the DNA in the nucleus of the cell. So our cells have a nuclei. These nuclei have DNA inside, which is the genetic information. And the hypothesis that we accepted scientifically is that the damage of the radiation to the cell starts from the damage to the DNA in the nucleus of the cell. So what happens is that you have a radiation. This radiation, it can interact directly with DNA and can break the strand of the DNA. And also the radiation can also form free radicals, which are molecules, specific molecules with oxygen and hydrogen. And what happens is that these free radicals, they can also break the strands. So of course, the more strands of the DNA I break, and the more is the damage to the cell. So at low doses, so when we are exposed to the background natural radiation on Earth, cells, we are bathed, there is interaction that is incident on us, okay? But the cells can repair the damage rapidly. At higher doses, so at higher doses instead, the cells, at higher doses instead, the cells may mutate, eventually to cancerous cells, or die. And here we have then at higher, instead then at very high doses, the cells cannot be replaced fast enough and the tissues fail to function. And in that case, we have radiation sickness or even death. Here, this slide shows the core of the problem. So let's consider a DNA strand that is represented here on the left. And let's do an experiment where we irradiate cells with different types of radiation, and we count the numbers of when the DNA helix gets broken. Because the more breaks, that we call them double-strand breaks, the more breaks we have, the more damage we are causing to the cell. On top here, in figure A, you can see the number of double-strand breaks in a cell caused by gamma rays, okay? And you can see that the double-strand breaks are distributed more or less homogeneously. Instead, if you see in the middle picture, you can see a nucleus of a silicon, and you can see here that the double-strand breaks, they're not any more sparse, but actually they are concentrated in a specific region. And then on bottom, it's the iron track, an iron track that goes through, again, a nucleus. And you can see that the more and more the damage is more structured. So this means that if you have a nucleus like of iron, silicon, which have a high atomic number, have a high number of protons, let's say, what happens is that you have a more structure damage. And we say that the track structure of that radiation is more dense. And the damage of an iron nucleus is a lot bigger than gamma rays, okay, if we give the same dose of radiation. On the right, you can see measurement of the track structure of different nuclei. Left, protons, so protons, you can see the track. And look on the right, you have iron. And you should appreciate how the track structure of iron is a lot more complex, let's say, and dense. So ions, heavier the nuclei, the more structure is the damage, and let's say it's also more, and the effect is larger. The problem is that still there is a lot of research to understand which is the effects of radiation like the silicon, iron nuclei on the human cells. Now, let me introduce the dose equivalent. So the dose equivalent is a physical quantity that we use to quantify the damage of radiation. So dose equivalent is a dose, so is all the dose that is given by the radiation in the body times this radiation weighting factor that takes into account the different types of radiation produce different damage. It's measured in sieverts, and I will use millisievert, which is 1 sievert divided 1000. I tell you, this is all the physics you need to know, okay, for my talk. The background radiation in Australia in 1 year is about 1.5 millisievert. One chest X-ray is a 0.1 millisievert, so it's 1/10, and one full body CT scan is 10 millisievert, and the radiation worker in Australia can be exposed to 20 millisievert of radiation, so 20 times higher than the background radiation. Now, my question is, and I would like that if you can go to Vox Votes, I would like to ask to you, in your point of view, which is the dose equivalent of 6 months on the International Space Station with respect to the annual background radiation in Australia? 10 times lower, the same, 10 times higher, 100 times higher, or 1000 times higher? This is my question. So connect again to live.voxvote.com and please answer to this question. With respect to the annual background radiation in Australia, the dose equivalent of 6 months on the International Space Station is about here we have the people have a different opinion. Well, I tell you that is about 100 times higher. And now I will ask you this question. With respect to the annual background radiation in Australia, the dose equivalent of 3 years of emission to Mars is? Ten times, 100 times, 1000 times, or 10 times higher. Well, good. The major part of you got it right. Is 1 times higher. Okay. So, when the dose is below 20 millisievert, which is the dose, the annual maximum dose for radiation workers in Australia, the doses are low and tolerable. When instead we have 100 millisievert, that is about 6 times, which is corresponds to about 6 months on the International Space Station, we have a higher risk of cancer, okay? 1000 millisievert, which is the one that has been estimated with the mission Curiosity on Mars, we have a 5 higher chance of cancer. At high doses, which means above 2000, we have acute radiation sickness, and then from then, when we have higher values, actually a person can die within a few days. So these numbers, you say, okay, fair enough, as long, you know, that we know that the dose, if you go to Mars, is only 1000, well, there is some risk of cancer, but, you know, maybe we can deal with the risk, it's fine. But actually, the fact is that we must make sure that our measurements are accurate. And then I will go back to it on it. So galactic cosmic rays is this background that bats the solar system, and the galactic cosmic rays are this background that can cause late effects like cancer, disease to the central nervous system and cardiovascular system. And in a mission to Mars, let's say that the NASA accepts for the astronauts a 3% excess cancer risk with respect to the public for astronauts on the International Space Station. And we think that for a mission to Mars, this excess cancer risk instead increases to 4%, 5% for male astronauts, and 7% for female astronauts. Female astronauts have a higher excess cancer risk because females have a higher risk of breast cancer. You have to know that astronauts are radiation workers. There are some limits, career exposure limits that are defined for NASA astronauts, and therefore it's not possible to send astronauts in space and not take care about radiation protection and how much dose they receive. So as you can see here, a female astronaut, age of 25 years old, the career exposure limit is 1000 millisievert, which is exactly what we estimate that is one mission to Mars. Of course, we can, interestingly, if you see this table, you see that the doses which are allowed increase with the age. And this happens because if the astronaut is younger, because the lifespan is longer, there is a higher risk to have cancer. And females, as I told you, have a higher risk to have a breast cancer, and therefore the limits of radiation, the legal limits of radiation for them are lower. So there are two key issues. Key issues here. One is to be able to measure accurately the radiation, okay, because we must make sure that we know exactly which is the dose that the astronauts encounter in space, in a mission. And the second is to define and design appropriate shielding solutions to radiation. So summarizing, the probability of developing cancer is, because of galactic cosmic rays, is 1 in 200 people for a 6-month mission on the International Space Station, and 1 in 20 people for a 3 years missions to Mars. So as you can see, a mission to Mars can be very risky by a radiation exposure point of view for galactic cosmic rays. Then we have also solar particle events, because the sun has this cycle of 11 years of activity, and there are periods where the sun emits a lot of solar particle events. So during a solar maximum period, about we have several solar particle events per day, and to less than 1 per week when the sun is quiet. Now we are in a minimum, but keep in mind that the missions to Mars for astronauts are all designed in maximum solar activity, because when we have a solar maximum activity, yes, we have a more solar particle events, but the galactic cosmic wave background is lower. And this because, in a certain sense, the solar wind swaps away the galactic cosmic radiation. The problem of the solar particle events is that intense solar particle events can produce very acute radiation effects, eventually bringing the death of astronauts within 45 minutes, okay? So this is the problem of solar particle events, is that they are difficult to predict, and we need to design shielding solutions to be adopted on the space vehicles in order to protect the crew from them. You have to think that in 1972, the two Apollo missions 16 and 17, they were done, but between the 16 and the 17, there was a very intense solar particle event. And if there was a crew going to the moon, exactly when there was the solar particle events, well, the crew would, that would be a fatal event for the crew of the Apollo mission. So I told you what we can do. We can design powerful and accurate radiation monitoring system or design shielding solutions. And I want to show to you briefly our research that we do in how we design this accurate radiation monitoring system. So we needed to be able to predict the effect of radiation in astronauts. And at the Center for Medical Radiation Physics, which is led by distinguished Professor Anatoly Rosenfeld, we developed silicon microdosimeters. They are sensors. Here you can see electron microscope image of silicon microdosimeters. This is an array. The sensitive parts are these cylinders here, and they mimic an array of cells. We are not made of silicon, fair enough. The astronauts are not made of silicon, but we can convert the measurements that we do in silicon to human tissue. And we studied this technology. Now we studied with the NASA and now also with the European Space Agency. And we are proposing it as a low maintenance, portable, easy to use detector that the astronauts can stick on their spacesuits, and we can measure the effects of radiation. And this technology, the advantage with respect to other ones, is that it is very powerful in a mixed radiation field. And space has a mixed radiation field because you have protons, you have silicon nuclei, iron nuclei, helium nuclei, and so on. And we designed this detector for space and aviation application. We are a large team dedicated to space. We collaborate in Australia with the Australian National Technology, Australian Nuclear Science and Technology Organization, ANSTO. So what we do, we irradiate our detectors in facilities around the world, like NIRSI in Japan. We irradiate our detector with a very high energy beams here of iron ions. And we want to study the response of these detectors and see how they work. But why do we need to go to Japan? Well, we need to go to Japan because there is not such a facility in Australia. There are in Japan, there are in Europe, and there are also the Brookhaven National Labs in the US. And we assess these, so once that we test our detectors at ANSTO, then we have staff that goes in accelerator facilities around the world, irradiate the detectors, and then we see and then we test them. And then we irradiate them also in flights to Antarctica because we propose this technology not only for radiation protection of astronauts, but also for pilots, because remember, when we are on a flight, anyway, there is more radiation. So this is an experiment that was done by our students. Stefania here is my PhD student, and they take measurements. You see they have their computer, and here the silicon microdosimeters are here in the bottom. You can see that there is people. Actually, this is a touristic flight of Qantas, and you can go and visit Antarctica from Sydney to Antarctica, and coming back is 15 hours. And you will find also our students and staff that take measurements and explain the effect of radiation in humans to the passengers. Here you can see more a close-up. These are our chip, and we take measurements of radiation. And so far, we had very good results with our technology. Now, what do I do in all this? Which is my role in this study of the radiation effects in these novel detectors called the microdosimeters? I am an expert of radiation physics simulations, in particular in a software which is called GEAN4. This is my team on the right at the University of Wollongong. So GEAN4 is this simulation software that describes radiation physics experiments, which is developed by an international scientific collaboration. I'm part of this collaboration since 2002, and my contribution was in particular to develop software tools in GEAN4 for medical physics applications, including radiation protection of astronauts. So keep in mind, GEAN4 has been used to model the particle interactions in large high physics experiments, like the Large Hadron Collider at CERN, then in medical physics to improve radiotherapy treatment. And part of my research is also in this topic, but we'll not talk about it today. And finally, in space. This GEAN4 is the simulation radiation physics tool, which is adopted as a standard by the European Space Agency. And all these missions have been characterized with GEAN4. But why do we need to be able to simulate in a software the interactions of radiation in space with this technology? For various reasons. The first one is that we want to study the effect of radiation on electronics and human beings. We want to characterize these radiation sensors before we launch them in space, because it costs a lot of money to send sensors in space. So we want to make tests as much as we can on the Earth in order to improve them. And finally, we use simulations to perform studies which are not possible with the current particle accelerator technologies. So I told you, we irradiate we do experiments in accelerator facilities. 1 hour to irradiate a sensor costs $2,000, $3,000, unless you have some research collaboration. So they can be very expensive experiments. But still, these accelerators don't manage to reproduce the complexity of the space radiation environments. Instead, radiation simulations allow to us to study the effect of radiation in sensors. Of course, we must make sure that the physics models that we use are correct. And this is also part of the research. Then my research is to characterize in microdosimetry for space radiation protection, is to characterize the novel microdosimeters by means of simulations in space radiation fields, but also to understand the results obtained in experiments in accelerator facilities in order to improve the design of the device. And this is the model in our simulation of our silicon detector. Then we irradiated in a GEAN4 simulations with a particle beam of interest. Here the blue line is a proton beam. You can see all these secondary electrons that are generated. And this is an example of a simulation. Then what we do when we perform experimental measurements in nuclear facilities, we simulate the same experiments, and we try to make sure, we want to make sure that we get the same results between the experiment and the simulation. And then finally, once that we validated that our simulation is correct, we can model space radiation environments like the one of the International Space Station, like we've done in this study with Stefania Peracchi. We modeled the Columbus module where the astronauts are, and we modeled the response in our silicon microdosimeter. And then we consider the typical mission of 1 day on the International Space Station, and we found again good agreement with viable experimental measurements which are in the literature. So now we are pretty confident that our model is correct. And now what we will do soon is to model the radiation environments of the moon and then Mars and study the response of our detector. So we are developing at the University of Wollongong powerful technology, silicon microdosimetry for radiation protection of astronauts. We use radiation physics simulation to study the radiation protection of astronauts. And I would like that you answer to my last question for today. And then, and the question is this one. Let's see. After this talk, would you go to Mars? Yes, and the seminar did not change my mind. The seminar changed my mind and my answer is no. The seminar changed my mind and my answer is yes. My answer was no before and after the seminar. So please answer. You have 30 seconds. Let's see, I'm very curious to see your answer now. Yes, and the seminar did, okay, very good. So this seminar did not change your mind, which means that is good. You are very motivated in it. That is very good. Then let me just give you last information. If you don't want to go on Mars, anyway, you have a great opportunity. I read today that we are back into tourism on the International Space Station. So if you answer no and you want to have a touch of what can be space exploration, maybe if you have to spend between 20 and 35 millions of American dollars, you can go on the International Space Station and you can have a little 8 days there as a tourist. Now, finally, where to find me? This is my webpage. This is my email. I'm the academic director of the Bachelor in Medical and Radiation Physics at the University of Wollongong. And I would like to mention to you that we also do year 11 and 12 in-depth studies in our research team in radiation protection of astronauts, but also in other topics. And we are very passionate about public outreach activities. Let me acknowledge Stefania Peracchi, my PhD student that did 90% of the work that I showed today. And let me thank Anatoly Rosenfeld, Lynn Tran, and David Bost of the CMRP Space team that support me a lot in my work. And thank you very much for your attention. I see that there are many questions. I will see the chat.
Thanks, Susanna. We'll leave it to you. Can you see those questions? Did you want to?
Yes. From. Okay. Okay. Oh, thank you for your. So I don't see the questions, guys.
You can't see the Q. Can you see the Q&A?
Ah, the Q&A.
Yes.
I was in another. Okay.
Yeah, not the chat.
Does Mars' lack of magnetic field suggest it is geologically inactive? Well, this is okay. In the past, scientists think that in the past there was a magnetic field, okay, but then it disappeared and we do not know why. Okay, now is it geologically inactive? We don't know, but maybe you are right that maybe there is the lack of magnetic field because because it's a geologically inactive. Maybe, but the problem is that we do not know it. So I'm sorry, I can't answer your question. It's a mystery. I am a mycologist. Allora, this is on fungi. Yes. I can. Okay. Can we bring crops on Mars mission? They're still not brought there, but on the International Space Station there are experiments with crops. It's not easy, okay, to bring crops on Mars missions, because first of all we could also bring some fungi. We could also bring you know, some yes, fungi or other organisms that actually would contaminate the Mars environment. But definitely there is a lot of study on crops in the International Space Station, and then the idea is to cultivate crops on the Moon and then on Mars. Yes, how to protect astronauts? Well, for the on the flight, what the idea is to have in the inner core of the vehicle a cylinder or a room, let's say, surrounded by at least 75 centimeter of water or polyethylene. It must be hydrogen-rich material because it stops better some radiation. And so what happens is that when there should be a monitor that says to the astronauts that there is a solar particle event incoming. So then the astronauts in a mission to Mars as designed by NASA will be no more than 6-7 people. So then these people have to go inside this shelter protected by this 75 centimeter of hydrogen-rich material and wait until the solar particle event is gone. Because during the flight, that is the higher risk. The galactic cosmic ray backgrounds, you will always have it, okay? You can put 1 kilometer of LEDs and you will still have radiation that is incident on the astronaut, because unfortunately these the galactic cosmic rays they span a lot of orders of magnitude in energy. It's basically impossible to stop them. So what we can do in the flight is just to have this inner shelter in the case of an intense solar particle event. Concerning instead how to protect astronauts on the Moon and on Mars, one of the hypothesized solution is to use lava tubes, which are natural caves, which you can find both on Mars and on the Moon. So basically the shelters of the astronauts would be underground, because only rock, let's say, can protect as much as we need astronauts from the harsh radiation environments. How accurate is the movie The Martian? Well, I read the book, I watched the movie, and honestly, I found that it's one of those that is closer to reality. So it's very well made, but still, I think, for example, the Earth, you know, where they cultivate the potatoes or in the Martian, actually the Earth should be brought from the Earth, I think. Because you have to know that the soil on Mars actually is poisonous for us, and then it's rusty. Would you really cultivate your potatoes in a rusty soil? So So potatoes, I'm not sure about the quality of the potatoes on Mars. I'm losing. But then for sure I wouldn't build an astronaut shelter on the surface of Mars. I would build a shelter underground. But I have to say that in general, that movie is the most close to reality than a lot of other movies of science fiction that I watched so far. What happened to the Mars One mission, which was going to be funded by private enterprise? Yes, you're right. There are also private enterprises of Mars One. Who knows what is going on? Honestly, I'm not very interested into it because ethically, I don't think. I mean, the Mars One is really to build a colony on Mars, and in my point of view, we are still not at the level. Not of the technology, but also to understand which are the effects of that environment on astronauts. So in my point of view, and this is my personal point of view, I like to mention that this is my personal opinion, it's still a very, very dangerous. I mean, if I had to study the astronaut's health, I would like to make sure that an astronaut goes to Mars and we can bring this person back. I wouldn't like to send people to death, honestly. So that's why, in my point of view, internationally, there is also a lot of work to do around ethics of space missions, because in my point of view, we are lacking in that. Okay. If so many countries investigate where or which organization will collect all the properties and develop a final product. So a question is about who will develop the final product for the astronauts, because actually it depends. For example, the European Space Agency is funded by the European community. So whatever is produced within the European Space Agency is given back to society and the two companies that operate in Europe. NASA I'm not sure about NASA works, but typically depends on the intellectual property of the technologies and on the patents. So it's a little bit difficult to say who will develop the final product. Would outposts on Earth's moon provide similar conditions to the moons of Mars? Yes, the Earth's moon, it's an excellent outpost in my point of view, because it's enough close to the Earth. So in case of a problem, a mission to the moon more or less is 8 days in total. So I think that it's a lot more feasible now, and in my point of view also technologically is a lot closer and more realistic to build an outpost on the moon, because we have the technology and then we have to study how to build a shelter on the moon, use the lava tubes. There is still the problem of microgravity, because microgravity can really, the effects of reduced gravity can be really detrimental. Is it possible to make a radiation-proof material? No, it's not possible, unfortunately. There is not, because the radiation energy really, they span a lot of order of magnitudes. It's not possible, but scientists study. We call them passive shielding, like you mentioned. Graphene is studied as a material to use in astronauts' spacesuits, rock is a passive shielding. But another solution is to use active magnetic fields. Active magnetic fields that you can have to protect this active magnetic field that surrounds the space vehicles and diverts the tracks of the particles. The problem is that still we need the super magnets, and this equipment would be extremely it would be heavy. So there are still some technological challenges, but also active magnetic fields are studied as a possible means to shield people from radiation, astronauts from radiation. Is the moon protected by Earth's magnetosphere? No, unfortunately no. So also the moon has a very harsh radiation environment. Maybe the best would for the solar particle events, let's say, is to plan a mission that the astronauts are on the nights. As you know, the rotation of the moon around its own axis is more or less 30 days, okay? So as long as we plan a mission of less than 15 days and to stay during the nights on the moon, that would help, and then also be underground. What was your reaction to watching scenes of workers working at the Chernobyl site? Actually, you have to know that distinguished Professor Anatoly Rosenfeld was one of the first that went to Chernobyl to check the level of radiation. I was a kid, I was living in Italy, and for sure to know that there is poison is yes, it is a drama, and the fact is that the nuclear power, in my point of view, is as the technology is going, is in my point of view, and again I express my personal opinion, is not a sustainable solution. I hope that the other forms of energy will be used more, and I think that the technology is doing great steps in that direction. But remember that, yes, there can be very bad, there can be accidents like Fukushima, like Chernobyl, but remember that also radiation is used every time you go to have an X-ray chest, and is also used in radiotherapy to cure cancer. So, radiation is not good or bad, it is the use of radiation that we use that is important.
There was a question at the top, sorry.
Yes, sorry. Yes.
About Earth applications.
Earth applications, what we...
Oh, just in the Q&A, maybe you can't see it. Has there been any interest in what you're researching for applications here on Earth? And I should mention,
yes,
we're running out of time, so we'll just take a couple more questions.
Yes, okay. So yes, now the study of new materials, that is an application. Anyway, all the technology that we study in space, then as an application on the Earth, and it can be in material science, in biology, medicine, also study psychological effects of living in isolation. So yes, there are a lot of repercussions at the end also on our life on the Earth. Then I'm interested in the nature of dark space, that all kinds of ways can survive and travel in different ways, we say, to be guarded for us. Dark space, okay, here I'm a little bit out of my feet. I don't really understand this question. I'm sorry. We can create an Earth environment. Maybe I will just answer to what I think in this question.
Go for it.
Yeah, like an Earth environment. Well, to create the Earth environment is extremely difficult. It's not possible. Yes, still, no, it's not really possible.
All right, a nice definitive answer at the end there. Thank you so much.
You're welcome.
Thank you so much to everyone for attending. Much appreciated. Enjoy the rest of your Sunday afternoon. We've got everyone coming up. If you go to our website, scienceatthelocal.org, you can register for a couple in the next 2 weeks on bee and insect behavior, as well as on medicinal properties of honey. Kevin, did I miss anything?
No, that's it. Thanks, Susanna. Great talk.
Thank you very much. Thank you for your attention.
See you all next
So
time.
See you
I
next
stop sharing. Do I close the recording? Yeah.
Sure. We're going to try and make it available for those still on the line. So stay tuned. We'll let you know how that goes.
Okay.
Okay.
So,
Bye, everyone.
okay, bye. So I will send you the recording once that is.
Yeah, we'll be in touch. Yeah.